I'm sharing my screen. Just check and let me know if the screen is visible. Yes, is the screen visible?
Yes, sir.
Okay. So good morning, students. Let us continue the sorting technique that we were discussing in the last lecture, that is quick sort. To quickly revise, we have seen that quick sort is another method of divide and conquer, where we keep on dividing our problem into smaller parts until we reach to the smallest problem of sorting. The smallest problem of sorting in case of quick sort is a problem in which there are no elements or there are one element. No element requires no sorting, whereas one element is by default sorted. So in this, the division takes place on the basis of partitioning, and this partitioning is done with help of a special element called as pivot element or pivot element, we can say. There are different ways or different strategies of picking pivot element. One such strategy that we are discussing in our curriculum, that is picking the first element as the pivot element. So in our example, you can see the element which is marked in yellow, that is 17, was the pivot element. Then we take two references, I and j. I is the immediate next number and j is the last number. Always we try to maintain smaller numbers on I and greater numbers on j. If we don't find a smaller number on I and a greater number of j, then we go for interchanging of these two numbers. And after interchanging, we do I plus plus and j minus minus. We continue this process till I and j are not crossing their boundary. So while I is less than equal to j. The moment I and j are crossing their boundaries, we are going to swap the number present at j with the number pivot, which we can see is happening here in the last stage where we are swapping 17 and 9. That time we were swapping the element present at j with the element present at pivot. This completes our first partitioning method. So when we complete this first partitioning method, now we are doing again quick sort from original low to j minus 1, we can say, because now we know the j is stopping at this particular position, right? So we have to again call quick sort from 9 to this 10. So what is this position? This will be j minus 1. And again we have to call quick sort from this position, that is j plus 1 till high. And this will continuously happen, and there has to be some terminating condition for the recursion also. Okay, with this we had completed 3 partitionings in the last lecture and had asked till the last particular step. So let us quickly continue that example and complete. You all can verify in your notebooks, you must have solved it, you can verify. Next time we pick pivot, that pivot will be 11. That time I and j both will be at the same position, because problem is comprising only of 2 elements. We check whether the number at I is small. Yes, we stop. We increment. Sorry, we increment. So once we increment, what will happen? I will go to this position. Now I and j have crossed its boundary. Correct. I and j have crossed its boundary. Correct. Then what we will be doing? We will be swapping the number present at j. We will be swapping the number present at j with 11. We'll be swapping the number present at j with 11. So swap will be happening. Swap will be happening. And this is how your elements will look like. In which 17 is already sorted. Then 12 is sorted. 9 is sorted. And with this now 11 is also sorted. Now 10 doesn't require to be sorted because it is only a single element. So this part is also by default getting completed. This part is also by default getting completed. Within this two, now 13 will be picked as pivot, next pivot. There will not be any swap happening and answer will remain same, and 13 will turn out to be sorted in the next stage. 16, as it is a single element, again this element will also not require any sort, will be treated as sorted. In the later stage, 22 will be treated as pivot. 22 will be treated as pivot. When 22 is treated as pivot, I will be here and j will be here. Whether the number at I is less, yes, so I plus plus. whether the number at I is less, yes, again I plus plus, I and j have crossed its boundary. Am I audible, students? Yes.
Yes, sir.
Yes,
Yeah.
sir.
I and j have crossed its boundary. After the I and j are crossing their boundary, then we copy all the elements down. Then we swap j. So 21 will come here, 22 will go here. And right hand side there are no elements remaining now. So that doesn't require any sorting. Left hand side will have one pivot element. That pivot element will be 21. And in that stage, 19 will be swapped with 21 in that particular. So with that, 21 first will get completed. And as 19 is a single element, again that will not require any sorting, that we treat it as complete. And this becomes our final sorting result. This becomes our final sorting result. These steps understood, my dear students of quicksort? Is anyone having any doubt, any query? We have already seen this in last lecture, right? Now, my dear students, there will be a homework for you people. I'll be giving you pseudo code now today for quicksort. Now, slowly your programming skills should improve. So I am giving you hints of how to write this program. Last time also during merge sort, I had given you the main logic of merge, and I have given you how to give recursive calls to merge sort. Intentionally, I have kept the terminating condition code empty and I'd ask you to complete it. But I am getting request from some students telling, sir, we are please tell us that logic. See, that much part is given to you as an homework. Okay, so try to make effort. See, if I tell you each and every whatever answer I'll tell you, then it will stop your thinking process. I want you people to do it. Okay, so slowly it has to happen, right? So some codes I'll teach, some codes you have to complete it. That will help you to build your logic also. Every code if I try to teach you total 100%, then that will not help you in improving your programming skills. Okay, so in quicksort, merge sort, these sorting techniques, we don't have any application problems as such over here. So that's why I'm keeping some part of these codes incomplete so that you can test it. Because in case of stack queue and linked list, there were application programs. So I used to teach you complete code and some application programs I used to give you as a practical assignments. But here the same programs you are going to try in your practical assignments. So that's why intentionally for few programs I'm keeping few portions, and those portions are not big portions, hardly 1 or 2 lines of code they are. So try to work on it, try to work and try to improvise on your coding skills. Okay, now when it comes to quick sort, we are working on partitioning. As I told you, in partitioning what we do, we have one element that is pivot element. Initially, what is this pivot? That pivot is treated as low only, right? We have one element that is high. What is this high? Initially that is low plus 1. And initially we have j. What is j? That j is high. Now this partitioning will get input in the form of low and high. This partitioning will get input in the form of low and high. It will get input in the form of low and high. Now once we get this, what we are supposed to do, my dear students, we are checking whether the number present at I is less than number present at pivot, and number present at j is greater than number present at pivot. And all this process continue while your I is less than equal to j. All this process continue while your I is less than equal to j. What we check inside? We check whether the number present at pivot is less than number present at I. Whether it is less than number present at I. If it is, then what we do, my dear students? We simply do I plus I plus. Similarly, what we do on right hand side? We check whether the number present at j, whether it is greater than the number at pivot. So only thing is I have written it in different. Sorry. I have written it in wrong way. Whether the number present at I is less than present at pivot. Whether the number present at j is greater than pivot. That is the case, we do j minus minus. Here we do interchange, but before interchange also we check. Before interchange also we check condition for crossing of boundaries. Okay, so here we will be having logic of swap. What will be swapped, my dear students? A of I will be swapped with A of j. A of I will be swapped with A of j. After we perform swap, we do I plus plus and j minus minus. We do I plus plus and once we come out of this particular while loop, at the end what we do, my dear students? We perform swap between A of j and A of pivot. A of j and A of pivot. So this is the pseudocode for partitioning. From where this will be called? This will be called from our main quicksort code. This will be called from our main quicksort code. What quick? And what this will do? This will return you an index. This will return you an index. What will be that index? That index will be the pointer j. Why we require that index? Observe this numerical, my dear students. When we completed the first iteration for 17, right? So for in case of 17, this j was stopping here at 6. J was stopping here at 6. Now next time I want to call again same quicksort between initial low to j minus 1, that is 6 minus 1, that is 5. And again I have to call quicksort on 7 to 9, that is j plus 1 to original high. So for that I need this index of my pivot, and this index is nothing but j. So that value j we will be returning from our partitioning function. That will be returning from our partitioning function. That value j will be returning from our partitioning function, because that will help us to again recursively call quicksort from original low to j minus 1 and j plus 1 to original high. Are you getting this? So when we do this, what we do, we call a partition here. We call a partition here, right? So how we call that partition? Partition function. This partition will happen between low and high. This partition will happen between low and high. What it will do? It will return you an index. It will return you an index. Again, what we are going to do? We are going to again call quicksort recursively. Again, we are going to call quicksort recursively. Where? Between low and j minus 1. Between low and j minus 1 and j plus 1 and high. That's what we did. What is this? This is nothing but solving left hand side. What is this code? This code is nothing but solving quicksort on left hand side. This is nothing but again solving on right hand side. And now, my dear students, this should also terminate somewhere. So for that, again we will require some terminating condition. This is again homework for you people. Try to practice recursion codes. Recursion codes are very important for campus placements. So you have to complete these conditions. Of homework. Rest logic is given to you, and this quicksort again will have low and high as input. Low and high as input, and from your main function, you are calling this quicksort initially. What you are passing initially, 0 and n minus 1. What you are passing initially over here is 0 and n minus 1. So from main, call goes to quicksort. From quicksort, call goes to partition. After partitioning is done, again call goes to left hand side. Recursively left hand side will be sorted, and then recursively right hand side will be sorted. So I'll just wait for a few moments so that you can take down this part of code. I'm just keeping it open, so if anyone has missed any part of pseudocode, they can note it down. can note it down, this part of code. I once again repeat, partitioning is done. While doing partitioning, the basic low itself is treated as pivot. In I is immediate next element of pivot. So I is low plus 1 and j is high. We continuously check a process while I is less than equal to j. We check whether the number present at I is less than pivot. If it is I plus plus, we check whether the number present at j is greater than pivot. We do j minus minus. We perform a swap only in case I and j have not crossed its boundary. And once we perform the swap, we do I plus plus and j minus minus. We do I plus plus and j minus minus. After we come out of this while loop, again we perform a swap between a of j and pivot. Once this is done, partitioning is completed, we return the index j. Now this j is used in recursively calling again quicksort from low to j minus 1 and from j plus 1 till high. This process will continue until there is 2 or more elements remaining in any of the parts. So if your left hand side or right hand side are having no elements remaining or only one element remaining, then we don't need to go for quicksort. So only quicksort will be recursively called now when low is less than high. Correct? It will be low is less than high. So that we have to check for the terminating condition. And this quicksort will be originally called from your main function, where initial value of low will be 0 and initial value of high will be n minus 1. Before calling this quicksort, first we will take input array A, correct? And then after calling this quicksort, again we will print array A, that will be your final result of sorting. But we have to make sure that the array A is declared as a global variable, because same array A will be used inside partition, right? So this array A should not be declared inside main, but this array A should be declared as a global variable. Then only same array A will be accessed inside main also, inside quicksort also, and inside partition function also. So try to complete this part of code whenever there will be a lab session organized under quicksort. Okay. Let us now move on to the next sorting technique. Okay, before we move on, let us see the analysis now. Okay, analysis is pending. So for analysis, my dear students, the three analysis for quick sorts, that is best case, average case, and worst case. There are three cases. For best case, the complexity is n log n. For average case also it is n log n, but for worst case it is n square. For worst case it is n square. Now I'll tell you what is that worst case. Imagine that you have been given for quicksort the initial input given, suppose it is in descending order. Suppose the original given input is in descending order. So what will happen if the original given input is in descending order? The first element will be picked as pivot element. Correct? First element will be picked as pivot element. This will be the greatest number. This will be greatest number, right? Now this greatest number at the end of first partitioning, what will happen? This will be going on the last position, because all the numbers greater than pivot should go on right and less than pivot should come on left. Due to that, what will happen? This greatest number will be going on last position, and at last position you will have the smallest number that will get swapped with the first number. That will get swapped with the first number. So the smallest number will come to the first position at the end of first partitioning, right? Now once the first partitioning is completed, on right hand side you will have no numbers. On the right hand side you will have no numbers, and on left hand side you will have n minus 1 numbers, and on the left hand side you will have n minus 1 numbers. So again this quicksort will be called on this left hand side n minus 1 numbers. Again the quicksort will be called on this left hand side n minus 1 numbers. Now in this n minus 1 numbers, again the pivot number that will be picked will be the smallest number, because that has come on the first position. Correct. So if we pick this number again, this number will be remaining at the same position. Left hand side there will be no elements remaining, and right hand side there will be again n minus 1 numbers remaining. And the same process will keep on continuing. And the same process will keep on continuing. So if your given input is in descending order and if you're applying a quick sort, that takes worst case scenario of n square because it tries to behave like bubble or selection sort, where the largest number or the smallest numbers are going at the extreme end. And that's why in such cases the complexity is assumed to be n square. But this is very rare phenomenon, that the input given is in the descending order and one is asking you to arrange them in ascending order. Only the possibility of having such kind of input for solving in case of quicksort will be very rare. Correct? Will be very rare. Now, my dear students, if we compare the complexities of merge sort and quicksort, I'll again quickly write down both the complexities. This complexity is for my quicksort, and for merge sort I'll write here again once again. If you remember in merge sort I had told you, all the three cases are n log n. All the three cases are n. So my question to all of you students is now, see, I have given you the table here of the complexities of quicksort and merge sort. Best case in both the cases is n log n. Average case in both the cases is n log n. Worst case in quicksort is n square and merge sort is n log n. Now, can anyone tell me which is a better sorting technique when I give you all these values? Amongst these two, which one is a better technique? Yes, my dear students.
Merge sort.
Merge sort. Okay, correct. So why you feel that merge sort is better technique? Can you tell the reason?
Because the complexity for merge sort is better than that of quick sort in the worst case.
Very good. In case of best case and average case, both looks to be same, right? So we cannot compare those two. But if we observe worst case, in worst case also merge sort is behaving like n log n, but quick sort is behaving n square. See, my dear students, how these values are coming. There are derivations for this. These derivations are not there in our curriculum. You have one more subject, as I told you, computer algorithms in third year. That time you are going to study in depth. So right now these values are coming. At least if you know these values is more than sufficient for you people in second year. Okay, but at least let us analyze that. Once we know the answer, we should be able to comment that which one is better and which one is not better. That much at least we can do here. So as correctly pointed out by these two students, that merge sort is looking better as compared to quick sort, because in best case and average case both are looking n log n. But in case of worst case, merge sort is n log n, which is better as compared to quick sort, where that is n square. But my dear students, we say that quick sort is the best sorting technique. What statement we make? We make a statement that quick sort is best sorting technique. Question comes why? Correct? We make this statement. So question comes why quick sort is best sorting technique. When we know that merge sort is behaving better in all the three cases. Actually, in the two cases, it is similar to quick sort, but in the worst case, it is better. So it is having extra edge over quick sort. But still, we claim that quick sort is the best sorting technique, because, my dear students, when it comes to comparing the two sorting techniques, we not only compare the time complexity, but we should also look at the space complexity. You remember in the first chapter, I told you that there are two types of complexity that we discuss: space complexity and time complexity. So all this logarithm and exponential, constant, these are time complexity related notations. So when it comes to space complexity, my dear students, in merge sort, if you remember, for sorting an array of size n, we used to take a temporary array. Because in case of merge sort, if you remember here, my dear students, in merge sort, merge, we don't do any swapping in the same array itself. We don't do any kind of swapping. We don't do any kind of interchange. We don't do any kind of displacement over here, my dear students. When we perform merging, for merging two sub arrays which are there in your array A, which is going from some low till mid and mid plus 1 till high, we require another array B of size n. Correct? If you remember in the code also, when we were merging and sub an array A of two parts, one part which was going from low till and another part which was going from mid plus 1 till high, we used to check I and J numbers and we used to paste that number in another array B. So for sorting n numbers in array A, we used to take another temporary array B of size n. Once we do that merging, we used to copy back the answer from B to A, because in the next recursion we should numbers in array A, right? So for sorting the array of size n, in case of merge sort, we require a temporary array of size n. But whereas in case of quick sort, we don't require. Here the swapping is happening in the same array. When you apply a partition, when you pick a pivot and we start checking the numbers with respect to that pivot, all the swaps that were happening, initially we swapped 21 with 12, then we swapped 19 with 16, right? Then further we swapped 22 with 9. So all these swap are happening in the same space. And for swapping, we are require only one temporary variable. For swapping, we require only one temporary variable. So if you are given n elements to sort, in case of quick sort, you only require one temporary variable. But whereas in case of merge sort, if you are required to sort n elements, you require another temporary array of size n. So when I consider this phenomenon of space complexity, with respect to space, if I say that you have to sort 100 numbers, so for sorting 100 numbers, I require another array of 100 in case of merge sort, whereas in case of quick sort, for sorting 100 numbers, I require only one temporary variable and storage for storing those 100 numbers. Correct? Original 100 numbers. If my numbers keep on increasing, if suppose I have 1000 elements to sort, so merge sort will require another 1000 array, which will be a temporary. So total memory required will be 2000 in that case for 2000 numbers. Whereas in case of quick sort, only original 1000 numbers required to be stored and one temporary variable is sufficient for us, right? So with respect to space, we can say quick sort is efficient as compared to merge sort. And my dear students, if we closely observe the phenomenon of worst case of quick sort, what was that phenomenon? I explained you the phenomenon. What is the worst case of quick sort? What is that phenomenon? When the given input is in descending order and you are asking the user to arrange it in ascending order. See, this is a very rare phenomenon to happen, right? So if I apply a probability, if I apply a permutation and combination for such type of input in real life, there will be a very rare chance that this kind of input is coming to your program and you are being asked to rearrange it in ascending order. Very rarely this kind of input will happen, right? So considering the permutation and combination, that this kind of input will be very rare that will come into the application. Most of the times the algorithm will behave into average case, right? Considering that phenomenon and also understanding the space requirements, overall it is commented that quick sort is the best sorting technique. Did you understand this, my dear students? Why we say that quick sort is the best sorting technique? Yes? Am I audible, students?
Yes, sir.
Yes.
Yeah. Yeah. Do we have roll number 12? Roll number 12.
Yes, sir.
Yeah. Why quick sort is the best sorting technique?
Uh, in the quick sort, only one array is required, but in merge sort, two array are required. And there is a worst case in a quick sort is n square, but it is a rare case.
Correct. So that situation is going to come very rare in our day-to-day life when the given input will be in a descending order and user is asking to arrange it in ascending order, right? So most of the times it will behave into the average case. So considering that fact and also understanding the storage requirement, overall it is commented. So sometimes, many times when in multiple choice questions, such type of question comes, which sorting technique is best sorting technique? So the answer is quick sort only. Okay. Overall, if I tell you, overall, we say quick sort is best sorting. But my dear students, if I ask you like this, that don't consider space complexity for a moment. Don't consider space complexity. On the basis of time complexity only, comment which is the best sorting technique. Then I will tell merge sort is better. Is it clear, my? If for a moment, if I tell you that forget space complexity, on the basis of time complexity, tell me, compare which one is better, quick or merge. So my answer would be merge, because it is clearly observed that in case of worst case, merge sort is having an edge over the quick sort. Is it clear? So multiple choice question or in gate examinations also, or in placement drives also, try to understand. If the question is told that in general we want to quote which sorting is best sorting technique, in general it is quick sort. But only with respect to time complexity, if someone is asking, then answer will be merge sort. Is it clear, my dear students? So this completes our fifth sorting technique, that is quick sort. This completes our fifth sorting technique, that is quick sort. We have two more sorting techniques in our curriculum, okay, for which we will not be having practical. Okay, so practicals you will be having only for these five sorts: bubble sort, selection sort, insertion sort, merge sort, and quick sort. Okay, practical in the sense practical implementation. So still I have not given any practical on bubble sort also, because you were supposed to upload the stack and queue implementations, dynamic implementations in last week, for which the deadline is given till this Saturday. After that, I'll be creating some links for the practicals based on this chapter. Still, I have not started any practicals. And see, my dear students, whatever practicals I am floating right now, all these codes are already being discussed during the lecture hours. That's why I didn't take any practical in the last week, and the Moodle was also not accessible. For me to check your programs, I need to have an access to Moodle. So I was not able to download and check because it was not accessible. But since day before yesterday, that is Monday, Moodle is properly accessible during night time also. Okay, so I have started checking your programs, but till the time if I give you some different programs, if I give you a similar program, I'll just be launching your practical problem statement on a Wednesday, and please see that you are uploading it in time. Please see that you are uploading it in time. Okay, because again taking a practical and again teaching linear search doesn't make any sense, right? Already if you are not able to recollect, please revisit the video recording which I have uploaded already. Okay, so coming back to our theory course, as I told you, we have seen five sorts up till now: bubble sort, selection sort, insertion sort, merge sort, and quick sort, for which you will have five practical implementations later on. We have two more sorting techniques in our curriculum. One is radix sort and another is heap sort. Out of which radix sort we will start today and heap sort we will discuss later on. But for these two, we will not be having any practical implementations in our lab. We will not be having any implementation in our lab, at least for our submission purpose. You can try those programs, but as far as submission purpose, these two programs are not there for your curriculum. Okay, radix sort and heap sort. Out of which for heap sort, my dear students, we need to understand the concept of trees. And we all know that tree data structure is there in the fifth chapter. Tree data structure is there in the fifth chapter, right? So, my dear students, once we study the chapter of tree, that time I will be taking your heap sort, because heap sort is based on tree data structure. So unless and until I teach you tree data structure, it doesn't make sense you to teach heap sort. So heap sort I will be keeping it pending. Once we complete the fifth chapter on trees, we will come back and we will discuss heap sort. So there are total 7 sort for our theory course. I again repeat, 7 sort: bubble, selection, insertion, merge, quick, radix, and heap sort. Out of which 5 we have completed. 2 are remaining: radix sort and heap sort. Radix sort I'll start right now, and heap sort we will be discussing after trees chapter. Heap sort we will discuss after trees chapter. Okay, so now we are starting with the sixth sorting technique, that is radix sort. We are starting with sixth sorting technique, that is radix sort. Is the screen visible? Is the Excel sheet visible, my dear students? Please, can you confirm?
Yes, sir.
Yes, sir.
Yeah. So we are discussing now the next sorting technique, that is radix sort. It is a very simple sorting technique, my dear students. It is very simple sorting technique. All of you just pay attention. Let us take few elements. Okay. Let us take few elements. I am taking those elements over here. Let me write those elements. Simultaneously, you can also write these elements in your notebook. Also write these elements. Just let me take the input. Yes. So I have taken these elements as input. Okay, some random numbers I have taken. Okay, so we have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers taken for radix sort. See, my dear students, this radix sort is also called as bucket sort in some textbook. Some other name is also there. It is also referred as bucket sort in some text. What happens in this? In this, there are buckets created. In this, there are buckets created. So I'll create those buckets over here. Okay. How many buckets are created? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 buckets created. There are 10 buckets created. So what are these buckets? These buckets are labeled with digits. So this is bucket number 0, bucket number 1, bucket number 2, bucket number 3, bucket number 4, bucket number 5, bucket number 6, 7, 8 and 9. So these are our buckets. These are our buckets. Okay. Now these elements, these numbers will be placed in these buckets in every iteration. In every iteration. Total there will be how many iteration? That depends on the data that have been given to you. See, my dear students, here in the data you have such numbers which are 3-digit at the most. Okay, 3-digit at the most, right? What is the greatest number in this? 992, right? And how many digits you have in 992? 3 digits are there. So you will have 3 iterations in your program. You will have 3 iterations. Iteration number 1, iteration number 2 and iteration number 3. So we are working in first iteration right now. We are working in first iteration. Now in first iteration, you have these 10 buckets which are labeled from 0 to 9. Which are labeled from 0 to 9. In first iteration, what we do? We observe the unit place. We observe the unit place of the given elements. What we do? We observe the unit place. What is unit place? What is unit place digit of 213? 3. Unit means this first digit from right hand side. Okay. What is the unit place digit of 152? It is 2. What is unit place digit of 314? It is 4. What is unit place digit of 157? It is 7. 164 it is 4. 193 it is 3, right? So unit place means the last digit of your given number, right? So based on that particular number, I am going to place that particular element in that respective bucket. So if I pick 213, what is the unit place digit of 213? It is 3. So I'll be placing 213 in bucket number 3. I'll be placing 213 in bucket number 3 on the basis of the digit placed present at the unit place. Next is 152. What is the unit place digit of 152? It is 2. So I'll place 152 in bucket number 2. I'll place 152 in bucket number 2. Are you getting this? Next is 314. So 314 I'll be placing it in the bucket number 4 because the unit place digit is 4. Next is 157. I'll place 157 in bucket number 7. I'll place 157 in bucket number 7. I'll place 157 in bucket number 7. Next is 164. Next is 164. So 164, the digit place is 4. So I'll place it in 164 will go in bucket number 4. Then I am 193. So it will go in bucket number 3. It will go in bucket number 3. Then we have 217. 217 will go in bucket number 7. 166. It will go in 6. Then 768. Then 768. So 768 will be coming in 8. 768 will be coming in 8. Then we have 687. Will be going in 7. Then we have 992. It will go in 2. This completes our first iteration, my dear students. This completes our first iteration. We have kept all the elements in the respective buckets. Now I am going to rewrite these numbers. Now I am going to rewrite these numbers from bucket number 0 to bucket number 9. From bucket number 0 to bucket number 9. And in one bucket, when I go, and if I have multiple elements in that bucket, the element which was added first will be added first here in my input. So I'll add 152, then 992, then 213, then 193, then 314, then 164, then 166, then 157, then 217, then 687, and finally 768. So I have rewritten the same elements again. Okay. Now this is output of my first iteration. This is output of my first iteration. This is output of my first iteration. Now again in second iteration, I'll have my buckets. I'll again have my buckets 0 to 9. Again I'll have my buckets 0 to 9 for my iteration number 2. For my iteration number 2. For my iteration number 2, my dear students, the output of first iteration will be input to the second iteration. Don't consider the original numbers. Now output of first iteration, that I have rewritten the numbers, right? This will be input to my second iteration. Here I will be checking the digits present at tens place. Tens place means the second position from right hand side. So that is one in 152 it is 5, in 992 it is 9, in 213 it is 1, 193 it is 9, and so on, right? And based on that digit, I'll be placing that particular element in that respective bucket. So now 152 will go here in 5, 992 will go in 9, 213 will go in 1, 193 will go in 9, 314 will go in 1, 164 will go in 6, 166 will also go in 6, 157 will go in 5, correct? Then 217 will go in 1, 687 will go in 8, and 768 will go in 6. So based on the digit present at tens place, we have placed this number in respective buckets. Again I'll rewrite the numbers. From bucket number 0 to bucket number 9. From bucket number 0 to bucket number 9. Right? So it will be written as 213, 314, 217, 152, 157, 164, 166, 768, 687, 992, 193. This becomes my output of second iteration. This becomes output of my second iteration, which is nothing but indirectly input to my third iteration. And now in third iteration, which will be my last iteration, because here we'll have, in this particular example, we have 3 iteration because we have only 3 digits, right? So we are going to check 100 place. We are going to check 100 place. We are going to check 100 place digit. While doing this check, my dear students, please see that you are referring to the input of the earlier iteration, output of the earlier iteration. If you apply this on the original input, then your answer will go wrong. Okay, so now what is 100 placed digit for 213? It is 2. It is 2, and so on, right? So it will go in 213 will go in 2, 314 will come in 3, 217 will go in 2, 152 will go in 1, 157 will go in 1, 100 will go in 1, 166 will go in 1, 768 will go in 7, 687 will go in 6, 992 will go in 9, and 193 will go in 1. Right? Again, we will rewrite the number from bucket number 0 to bucket number 9, one after the other. 152, 157, 164, 166, 193, 213, 217, 314, 687, 768, and 992. This becomes our final output of sorting. at the end of third iteration. Is it clear, my dear students, how we arrange the numbers in the bucket and how the sorting is happening in case of bucket sort? Is the example understood?
Yes, sir.
It is very simple. Only thing is, in every iteration, we check that respective digit of that particular place. First we check unit place, then we check tens place, then we check hundreds place, and if there are more numbers, then we will check thousands place, then 10,000s place, and so on. That place digit will be checked. Based on that digit, the number will be placed in respective bucket. The numbers will be rewritten from bucket number 0 to bucket number 9. The number which is added first in the bucket will be written first. See, if you observe, I write 152 first, then 157, then 164. Don't write it in reverse order. If you write it in reverse order, again your answer will go wrong. Okay. So in every iteration, the output of earlier iteration will be taken as input. And if you do it for those many number of iterations which are expected, actually depends on the data which is given as input. If you have an element with 4 digits, then you will have 4 iterations into it. And my dear students, some students may have doubt. Suppose, sir, they may have a doubt like, sir, what if there would have been an extra element 92 in this? 92. Suppose there is another element 92 here in the input. So 92 is not having 3 digits. 92 is not having 3 digits, right? So what will happen? In the first iteration, 2 will be referred. In the next iteration, 9 will be referred. And in the third iteration, for hundreds place, we will be considering it as 0. Correct? We will be considering it as 0. Are you getting this? So if some elements are not having same number of digits, it may happen na, that some numbers are 4-digit numbers, some are 3-digit numbers, some are 2-digit number. But if I am having a 4-digit number, so I'll have 4 iterations. But for those numbers who are not having those many number of digits, in those cases, for those particular iterations, we'll be treating that number to go in bucket number 0. As simple as that. Is it clear, students? So if 92 would have been there in this logic, now I don't add because it will change the entire answer. If 92 would have been there, then iteration number 1, it will refer to bucket number 2. It will refer to bucket number 2. Right? Then iteration number 2, it will refer to bucket number 9. And in iteration number 3, it will refer to bucket number 0. Because 92 will be treated in that case as 092. Don't treat it as 920. Some students treat it as 0 in the first iteration itself. 92 is a different number and 920 is a different number. If you imagine 92 and take 0 at the unit place, it changes the meaning of that number and you get a wrong answers for your sorting. So that extra padding of 0 that you are doing, it should be going on left hand side and not on the right hand side. Is the numerical clear of Radix sort, my dear students? Yes?
Yes, sir.
Yes, sir.
Yeah. So with this, we'll stop for today. We are already at 9:48. Okay. Let me download the attendance.